Good morning to all of you. In previous session, we have seen the system function of a LTI system, linear time invariant system, where we identified the system function from the difference equation as well as by using convolution summation. We have also seen one example where we identified the system function from the given difference equation as well as we identified the unit sample or impulse response. In today's session, we will be discussing inverse Z transform. Okay. So, in various sessions, we'll be discussing different methods for identifying the inverse Z transform. So, we'll be discussing three methods that are often used for the evaluation of the inverse Z transform. So the first method is direct evaluation by contour integration. Direct evaluation by contour integration. So this method is also referred as inverse Z transform by contour integral, or it is also referred as inverse Z transform by using the complex inversion integral. Or somewhere it will be also referred as inverse Z transform by Cauchy residue theorem. Okay, so basically in this method, this Cauchy residue theorem is used to identify the inverse Z transform. Okay, so this direct evaluation, so this method is referred as direct evaluation by contour integration. Okay, so in some context it is also referred as contour integral or complex inversion integral or Cauchy residue theorem. The second method that we will be discussing is expansion into a series of terms in the variables Z and Z inverse. Okay, that is positive powers of Z and negative powers of Z. So this expansion into series of terms method is also referred as power series expansion or long division method. Long division method. Okay, so the first one is direct evaluation by contour integral, second one is expansion into a series of terms, which is also referred as power series expansion or long division method. The third one is the partial fraction expansion. It's also referred as table lookup method. So these three methods for identifying inverse Z transform we'll be discussing in subsequent sessions. Today we'll discuss the first method, that is direct evaluation by contour integration or contour integral, complex inversion integral, or it is also referred as Cauchy residue theorem. So the first method is inverse Z transform by contour integral. Okay, that is by using Cauchy residue theorem. Okay, so as we know that the Z transform of discrete time signal x of n is represented as x of n having Z transform capital X of Z, and the formula for this is summation n is equals to minus infinity to infinity x of n into Z to the power minus n. Okay, so this is reversible process. That means we can identify x of Z using x of n, and even you can identify x of n from the x of Z. Okay, so identifying x of n from x of Z is called as what? Inverse Z transform. Okay, so in case of this inverse Z transform by using contour integral, this x of n, okay, inverse Z transform by contour integral is simply obtained by using formula x of n is equals to 1 upon 2 pi j contour integration. So it is a circle, right, with C has been indicated here. So this is called as what? Contour integration, right? So this is symbol for contour integration, right? Contour integration of x of z, okay, because we are identifying x of n from the x of z into z to the power n minus 1 dz. Okay, so this is the contour integration of x of z, right, to get the original discrete time signal x of n, right? So here this contour integration, okay, this integral, that is this one, this integral is referred as a contour integral. So what do you mean by contour? So it follows certain path, right? So basically a contour integral over a closed path, okay, it is a contour integral over a closed path C, okay, small c, that encloses the origin and lies within the ROC of x of z, right? So that means it will be evaluated for the values of z for which that x of z is finite, basically, because ROC only comprises the values of z where x of z is finite. Okay, so therefore this contour integral is simply taken over a closed path C, right, that encloses the origin. This contour integral is over a closed path C that encloses the origin and lies within the region of convergence of x of z, ROC of x of z. Okay, so simply C can be taken as a circle in the ROC of x of z in the z plane, right? So that is what this contour integral indicates, right? So more specifically, or in more simplified way, this contour integration, okay, what is the formula for identifying the inverse rate transform by using uh, contour integration? So it is x of n is equals to 1 upon 2 pi j, right? Contour integration of x of z, z to the power n minus 1 dz. Okay, it is the formula, right? So in more simplified manner, it can be simply represented as x of n, okay, is equals to summation. So these are the all poles, okay, all poles, those are simply denoted as zi inside the closed path inside C, right? So we'll be evaluating this summation for all values of poles for the given transform, right? So it will be simply evaluated as the residue of what, x of z into z to the power n minus 1 at the values of z is equals to all pole values, where this zi indicates the all poles, right? So again, in more simplified manner, you can represent it as x of n is equals to summation for all poles, okay? So this residue of x of z, z to the power n minus 1 is simply z minus zi, okay? That is z minus values of poles multiplied by, again, this x of z into z to the power n minus 1, okay, which is evaluated at z is equals to zi, okay. So this expression will be evaluated, the summation will be evaluated for all values of z is equals to zi. So these zi's are nothing but the values of poles, okay. And provided that the poles zi are simple, okay, this should not be complex poles, right? Correct. So if x of z into z to the power n minus 1, because we are identifying poles for this complete expression, okay, that is for x of z into z to the power n minus 1. So if x of z into z to the power n minus 1 has no poles inside the contour C, okay, that is inside the closed path C for one or more values of n, right? Or one or more values of n, then simply x of n is 0 for those values, right? So if x of z into z to the power n minus 1 has no pole inside the closed path, that is inside the contour C, right, for one or more values of n, then this x of n will be taken as 0, okay, for these values of n, okay, for these values of n. So this is how we'll be identifying the value of x of n by taking this contour integral, or by evaluating this contour integral by using Cauchy residue theorem. So inside this Cauchy residue theorem, this contour integral can be represented as the residue of x of z into z to the power n minus 1, which is evaluated at z is equals to zi. So that is according to the Cauchy residue theorem, right? So basically, in this method of inverse Z transform by contour integral, we're evaluating the inverse Z transform, okay, by using this contour integration formula 1 upon 2 pi j, where the contour integral over C has been taken of x of z into z to the power n minus 1 dz. So where this contour integral is over a closed path C that encloses the origin and lies within the ROC of x of z. So, but for evaluation of this contour integral, we are using this Cauchy residue theorem. So as per this Cauchy residue theorem, this contour integral will be evaluated as a summation for all poles. This summation is taken for all pole values inside C, right? Inside that closed path or inside the contour, where the residue of x of z into z to the power minus 1 has been taken at z is equals to zi. Okay, so this has been taken at z is equals to zi. So it will be evaluated for all values of poles where this residue is represented as z minus zi into x of z to the power n minus 1. It is evaluated for all values of poles, right? So provided that the poles zi are simple, this should not be complex one, right? And if x of z into z to the power n minus 1 has no poles inside the contour for one or more values of n, then x of n will be taken as 0 for these values of n, right? So we'll try to evaluate or identify one's inverse Z transform by using this contour integral method. So let's solve one example here. Okay. So in this problem, we have to evaluate the inverse Z transform. That means we have to identify x of n from the given x of z. X of z is given as 1 upon 1 minus az inverse for mod z greater than a. So this is nothing but the ROC mod z greater than mod a. Okay, so you have to use complex inversion integral. Okay, so in example it may be mentioned that you have to evaluate the inverse transform by complex inversion integral or contour integration or integral, right, or by Cauchy residue theorem. Okay, so the same process will be followed, okay, that I will be explaining here, right? So here the given x of z, the given z transform x of z is what has been given here. So x of z is equals to 1 upon 1 minus az inverse, right? So as per the complex inversion integral or contour integral method, okay, as per contour integral method, inverse z transform of x of z, inverse z transform of x of z is simply represented as x of n is equals to 1 upon 2 pi j contour integral of x of z into z to the power n minus 1 dz, right? So this is the formula. So in place of x of z, you can substitute this value 1 upon 1 minus az inverse, right? So this x of n will be simply 1 upon 2 pi j contour integral. In place of x of z, I can substitute 1 upon 1 minus az inverse multiplied by z to the power n minus 1 dz, right? So if I am simply avoiding the negative powers of z, okay, from this equation, so I can rewrite it here. So what we have x of n is equals to 1 upon 2 pi j contour integral of, what is that, 1 upon so it is 1 upon 1 minus az inverse z to the power n minus 1 dz. Okay, so if I am simply representing it as a upon z instead of az inverse, a upon z, so it will be z minus a whole upon z. So if I am sending z in numerator, so z will get multiplied with z raised to the power n minus 1, so it will be simply z to the power n. Okay, So here I can simply represent it as x of n is equals to 1 upon 2 pi j contour integral of what is that, z to the power n upon z minus a, right, dz. Okay. So this is how you can represent it, correct? So, but here, if you identify or if you consider this term, that is z to the power n and z to the whole upon z minus a. Okay, so in this case this n can be negative or it can be positive. So if it is negative, okay, so that means if n is negative, so it will have two poles. Okay, two poles at one will be at z is equals to 0 because it is negative, so 1 upon 0 is infinity, right? And another one will be at z is equals to a. So if it is at z is equals to a, so a minus a will be 0, right? So that means if n is negative, so it has two poles at z is equals to 0 and at z is equals to a. But if it is positive, so if z is n is positive, so pole will not exist at z is equals to 0 because for z is equals to 0 this value will be 0, right? And we have to consider these poles inside the contour. Okay, contour means the ROC will lie inside this contour, so that means that will be for some finite values. Okay, we will be considering pole values, right? So for positive values of n, that means the power of z is positive, so in that case the pole will be only at z is equals to a. Okay, that will not, the pole will not exist for z is equals to 0, right? So here we'll be considering two cases. Okay, in case 1 we will be considering n negative, and in case 2 we'll be considering n as positive value, right? So case 1, when n is less than 0, that means n is negative, right? So in this case, again, this x of n, what we have, it is 1 upon 2 pi j, right, with contour integral z to the power n upon z minus a dz. Okay, so this z to the power n, z minus a has, this particular term has two poles. Okay, at z is equals to 0 and at z is equals to a. Okay, so if you are substituting any one of these two values, okay, so if you are substituting z is equals to 0, as n is negative, so it will be 1 upon 0, so it will be infinity. And if you are substituting z is equals to a, so a minus a will be 0, so 1 upon 0 is infinity. So for these two values, this will be infinity, so therefore it has two poles at z is equals to 0 and z is equals to a when n is negative, right? So as per Cauchy residue theorem, okay, as per Cauchy residue theorem, the contour integral can be evaluated as, how it will be evaluated, so it will be evaluated as summation. Okay, so x of n is equals to, for all I, that means for all poles, so what we are writing here, so it z minus zi, okay, multiplied by this complete term, right, that is z to the power n upon z minus a dz, right, because that thing we are representing here, z minus zi, x of z into z to the power n minus 1, right? So we already multiplied this 1 upon 1 minus a z inverse with z to the power n minus 1. So after multiplication, that is 1 upon 1 minus a z inverse multiplied by z to the power n minus 1. So this one, that is z to the power n upon z minus a, right? So that will be evaluated for z is equals to zi, and the values of this zi will be, it can be 0 or it can be a, right? Correct. So we have to evaluate it for these two values, right? So here what equation we have? So we have this x of n is equals to, for all I, okay, we have z minus zi, z minus zi, I'm rewriting that equation, last equation, into z to the power n upon z minus a, right? Evaluated for z is equals to z. Okay, I will try to, as we are considering in case 1 n is less than 0, that means n is negative, right? So as we are evaluating it for negative values of n, so just for example, for n is equals to -1, what will have? So if I'm substituting n is equals to -1 here, so I will have x of -1, right? So x of -1 is equals to summation for all I, correct? So it will be z minus zi into, I'm substituting n is equals to -1, so it will be z inverse upon z minus e, correct? That is that z is equals to z. But as there are two poles, so I will replace this zi with what? 0 as well as with a. So there will be two terms, okay? So for x of -1 there will be two terms. First one will be for zi is equals to 0, right? So it will be z minus 0, again z inverse upon z minus a, right? So that will be evaluated as z is equals to 0, plus second term will be for zi is equals to a, right? So it will be z minus a, okay? So it will be again z inverse upon z minus a, and it is evaluated at z is equals to a. So first one is for zi is equals to 0, and second one for zi is equals to a. So wise we are replaced it with this zi with 0, okay, and this zi with a, okay. So there are two values of poles, therefore two different terms are there, okay. For three poles, third term will be added, right? So now if I am evaluating this, so this x of -1 will be simply, so z multiplied by z inverse will be 1, right? And it will be 1 upon z minus a, simply 1 upon z minus a, and it will be at z is equals to 0, plus, so this I can cancel, right? Z minus a will get cancelled, so it will be 1 upon z, right? 1 upon z at z is equals to a, okay. Maybe I'm substituting the values of z in this equation, so it will be minus 1 upon a, plus it will be, because here z is equals to 0, right? So it will be minus 1 upon a, and here z is equals to a, so it will be 1 upon a. So if I am finding it, the value of x of -1, so for n is equals to -1, x of -1 is 0, right? So similarly, if n is equals to -2, right, what will have? So again, as per this formula, that is x of n is equals to summation I z minus zi, z to the power n, z minus a at z is equals to zi. So for n is equals to -2, what I, so it will be x of -2 is equals to summation for all I z minus zi, z to the power -2 whole upon z minus a, right? That will be as z is equals to 0. Again, there are two values of poles, so I will be evaluating it for two different values of zi. So this x of -2 is equals to, so first I will substitute zi is equals to 0, so it will be z minus 0 into z inverse z minus a at z is equals to 0. Not z inverse, it is z raised to the power minus 2. Okay, so z raised to the power minus 2 upon z minus a. It will be for z is equals to 0, another for z is equals to a, so z minus a, again z to the power minus 2, so it will be z minus a, and it will be at z is equals to a. So again in this case, if you find it, so z multiplied by this z inverse, right? So it will be simply z inverse, and if you are multiplying it with z inverse, so it will be simply, if you multiply it, so z inverse will be in denominator, right? So it will be z to the power z square will be there, z square minus az will be there, right? So here I can simply represent x of minus 2 is equals to what I can write. After simplification, I can write 1 upon z upon, sorry, 1 upon z into z minus a, because this z multiplied by z power minus 2 will be z inverse, and that z inverse I am sending in denominator, so z in bracket z minus a will be there. So that will be evaluated for z is equals to 0, plus again this z minus a will get cancelled, so it will be 1 upon z square will be there, okay, simply, and that will be evaluated at z is equals to 0. So again, if you find the value of this expression, right, not for here, it is z is equals to 0 and it is z is equals to a, right? So if you get these values here, so it will be z square minus az, okay. So this minus az and this 1 upon z square, again this will be somewhere near to infinity if you evaluate it, right? Because this z square minus az, okay, again you will be substituting value of z is equals to 0. So if you are substituting value of z is equals to 0, so it will be 0, so 1 upon 0 it will be infinity, right? So it comes to infinity, but for negative values of n, if you again substitute it for again, so you can substitute values of n is equals to minus 3, minus 4, so it will be 0 somewhere near to infinity. So you can consider for negative values of n, okay. So for n less than 0, you can consider x of n is equals to 0 simply, because after evaluation it comes to 0, right? So in case 1 you have considered values of n negative, so your x of n will evaluate to 0, right, for negative values of n. Now we will consider case 2, right? In case 2 we consider for positive values of n, that is for n greater than or equals to 0, right? So again this x of n will be taken as it is, that is 1 x of n will be taken as 1 upon 2 pi j contour integral, right? 1 upon 2 pi j contour integral of z to the power n upon z minus a, right? Z to the power n z minus a dz, okay. dz, okay. So if n is positive, okay, so in that case there will be only one pole, okay. So this particular term, so this term has only pole at z is equals to a, so it will not have any pole for other values of z, it will have only pole at z is equals to a. So if I am evaluating this contour integral by using Cauchy residue theorem, okay, so again I can write x of n is equals to, for all I, z minus zi, right? Again it will be z to the power n upon z minus a, right, at z is equals to zi, okay. So as there is only one pole, So you can directly evaluate for it for z is equals to a. So I can write x of n is equals to z minus a. Okay, I am substituting the value of pole here. In place of z I am substituting a because it has only one pole. So z to the power n upon z minus a, and that will be at z is equals to a. Okay, this z minus a will get cancelled, so this will be simply x of n is equals to z to the power n, which will be evaluated at z is equals to a. So if I am substituting z is equals to a here, so x of n is equals to simply a to the power n, right? So that means for positive values of n, this x of n will be a to the power n simply, right? So therefore, if you combine these two results, for negative values of n, x of n is 0, and for positive values of n, x of n is a to the power n, right? So these two different results we have. Okay, we are interested in identifying the inverse z transform of x of z. So here we can conclude that, okay, for n less than 0, x of n is 0, and for n greater than or equals to 0, x of n is equals to a to the power n. Okay, so that means if you want to club this x of n, okay, for both these conditions, so you can simply write that the inverse say transform of x of z is x of n is equals to simply a to the power n. So I multiply here with u of n, right? Why I am multiplying with u of n, a to the power n into u of n? Because for negative values of n, x of n is 0, right? And for positive values of n, x of n is simply a to the power n, because u of n will be 1 for n greater than or equals to 0. So this is the required inverse Z transform by using contour integral or complex inversion of integral method, right? Or by Cauchy residue theorem. Okay. So in this today's session we have discussed there are three different methods for identifying inverse Z transform, that is direct evaluation by contour integration, which is also called as contour integral or complex inversion integral or Cauchy residue theorem. Second method is expansion into series of terms, that is power series expansion or long division method. And third method is the partial fraction expansion method. So we discussed the first method in today's session, that is inverse Z transform by contour integral. Okay, where we are using the Cauchy residue theorem for evaluating the contour integral, right? So here we are seeing one example where we identified the inverse Z transform of this x of z. Okay, x of z is given as 1 upon 1 minus az inverse. We represented it by using contour integral, and we have considered two cases when n is negative and when another case is n is positive. So for negative values of n, x of n is 0, right? And for positive values of n, x of n is obtained as a to the power n. So that two conditions has been clubbed here by multiplying the obtained x of n with u of n. For negative values of n, this x of n will be 0, and for positive values of n, this x of n will be a to the power n simply. Okay, so in next session we'll be discussing the second method of finding inverse Z transform. Okay, that is power series expansion method, that is nothing but the long division method. Okay, thank you for joining this session.